Hello and welcome to this video for basic sentential logic, informal fallacies, and cognitive biases. This video I'll be talking about material corresponding to section 2.3 of the textbook. And the topic is going to be assessing argument validity with a truth table. And I call this part 1 because what I'm going to do in this video and also in section 2.3 is to explain how to use a truth table to assess validity for some arguments in a way that hopefully makes what we're doing clear. But there's going to be a couple of issues with this particular method, and then later on we'll be sort of generalizing this approach to a way that doesn't have these problems. But so there'll be a part 2 of validity coming up later. But what I want to do now is first off just put the 4 truth functions up. So in the last video, we looked at the truth functions for negation, conjunction, disjunction, and conditional. And here I'm just putting the truth tables for these functions up here to remind you of them. This one could be just 2 rows because it's only a function of alpha and not beta, but you get the idea. Now, one thing we can do, and these will help us just remember what the functions are, is I could ask you a question like, if P or Q is true, but P is false, do we know anything about Q? Okay. So pay attention to this question here, right? So I'm giving you some conditions, and condition 1 is that this disjunction is true, P or Q is true, and also that P itself is false. And if those in that situation, do we know anything about Q? Well, yes, we know that Q has to be true, right? And why? Well, sort of think it through. If P or Q is true, then we know one of the disjuncts, one or both of them, has to be true, right? So let's look back up here at the disjunction. A disjunction is true when both disjuncts or either one of the disjuncts is true, but not when they're both false, right? So if we know that the disjunction is true, we know that one or more of the disjuncts has to be true. And if P is false, right, then that means that Q has to be true. That has to be the true disjunct that makes the disjunction true, right? So because of our knowledge of these truth functions, we can answer questions like this. We can ask and answer questions like that. Here's another one. If the conditional if P then Q is true, and the disjunction P or Q is true, can P be false? Is that possible? The answer is yes, P could be false. And here's how we know that. Why? Well, we know that if P then Q is true, so let's look up here at the conditional. If that's true, then here's the combination we can't have. We can't have a true antecedent and false consequent. We can't have P is true and Q is false, right? And if P or Q, if that disjunction is true, we can't have them as both false, right? So here's the disjunction. The disjunction is true. That means they can't both be false, right? So we're ruling out this combination, P is true, Q is false, and we're ruling out both of them are false. That leaves 2 possibilities. P is false and Q is true, or both of them are true, right? But the question was, can P be false? And yes, it can, right? P is false and Q is true is one of the possibilities that's left over once we make our conditions true, right? P could be either true or false. If you're starting to look at this and you're thinking, man, that's really complicated. I don't know. These are like questions you'd have on the LSAT where you're being given these weird relational conditions and then asked some question about some other thing. Could some other thing be true or not? don't worry about that, okay? Because it's going to turn out there's an easy way to answer these questions. So for instance, suppose, here's a question. If the conditional if P then Q is true and the conjunction P and Q is false, and also Q is false, can P be true? Well, we could reason through this one the same way we did the other ones, right? But it's going to be pretty complicated, right? And you have to keep a lot of things in mind and everything. But it turns out there's a much easier way to answer questions like this. Okay, so the first thing I'm going to do is I'm going to combine all of these truth functions onto one table. And I put a table like this up at the very end of the last video as just a summary of all of our truth functions. So instead of having these all on separate tables, I'm just going to put it on one truth table, right? So we still have all of the inputs for P and Q, and then just on each row, we know what the disjunction would be, let's say on row 1, where both disjuncts are true. So this is just summarizing all of our all of the truth functions. Well, now, if we use this table, let's look at a question like, if P or Q is true but P is false, do we know anything about Q? Okay. Well, to make P or Q true, we have to be on rows 1, 2, or 3, right? So P or Q, row 1, 2, and 3. So these are the situations where this first condition is true. P or Q is true. So rows 1, 2, or 3, these are the situations that make P or Q true. To make P false, we have to be on rows 3 or 4. So rows 3 and 4 are where P is false, or not P is true, right? P is false, not P is true on 3 and 4, right? Both conditions, so to make both of these conditions true, we're restricted to row 3. So row 3 is the row where both these conditions, P or Q is true and P is false, are true. So now I'm just going to put a green box around row 3 because this is where all of the conditions that we've set up are correct. Now that we know what makes the conditions correct, do we know anything about Q? Well, we're restricted to row 3, and Q is true on row 3. So the question is, if P or Q is true but P is false, do we know anything about Q? Yeah, Q has to be true. Okay. Let's look at this one. If this conditional is true and the disjunction is true, if P then Q is true, disjunction P or Q is true, can P be false? Well, let's look at the first condition. If P then Q, that's true on 1, 3, and 4. And P or Q, that's true on 1, 2, and 3. Right? So to make both of these true, we have to restrict our attention to rows 1 and 3. Right? Because 1 and 3 are the rows where both of those conditions are met. Okay, so now I'm just going to put green boxes here around rows 1 and 3 to just indicate that those are the ones we're paying attention to. And the question is, can P be false? Well, now we just look at the rows that we're interested in and see. Well, let's look at P. P can be true or false. So if we're just restricting our attention to rows 1 and 3, P could go either way. So P can be false. It could also be true. So these conditions leave it open as to whether P is true or false. But to answer the question, can it be false? Yes, it can. So you see what's happening here. The truth functions individually are they're not complicated, but if you started asking questions like this and you were trying to keep everything in mind in answering them, it starts to get tough really fast. But we can use a table like this to make our job easier because this table is sort of keeping track of all these things for us. What we do is we just find the rows where all these conditions are met, and then we answer the question by looking at those rows. and seeing what the possibilities for truth values of the statement we're asking about is. So this is the one that I said would be pretty complicated if we try to do it in our heads. It's actually not too bad if you try to do it in our heads, but it's pretty trivial if we just use the table, right? So the first thing we do is we find all the rows where the conditions are all met. So we want if P then Q is true, and P and Q is false, and Q is false. Okay, so first one, that's true on 1, 3, and 4. P and Q is false only on row 4, and Q is false on 2 and 4. And I won't draw squares around the rows, but you can sort of see here that the only row where all these conditions are met is row 4. Okay. All the conditions are met only on row 4, so I'm going to put a green square around that one. And then the question was, can P be true? Well, now we just look and see. Here's P. No, it can't be. P has to be false. When all those conditions are met, the only option for P left is to be false. Okay. And hopefully you can see now that no matter how complicated you made a question, okay, we could have if P and Q is true, but the disjunction is false, and, whatever, you could add them all up. All you have to do is you just go through, you find the rows where all the conditions are met, and then you just look at those rows to answer the question. Can P be true, for example? And here we know it can't be. It has to be false. So to answer a question like this, just to summarize, you find the rows where all the conditions are met, and then you just answer the question by seeing what the possibilities are on those rows. Okay? So that's what we did here, right? We had a complicated question. We determined what rows were those where all the conditions were met, and there was only one, row 4. And then we saw that on that row, P can't be true. It has to be false. Notice, though, that we can use this exact same method to ask questions about premises and conclusion of an argument, because those are just statements. What we've been doing so far is just asking about statements. If P or Q is true, but if P then Q is false, right? So those are just statements. And premises and conclusions are statements. So we could, for instance, if I gave you an argument like this, we could ask questions like the question that's crucial for validity. Now remember the definition of validity from chapter 1. A deductive argument is valid if and only if the premises are all true, the conclusion must be true. Well, now we can see if that holds, right? Because we can use the truth table to say, if this is true and that's true, does this have to be true? If the premises are all true, does the conclusion have to be true? And we do it the same way. We find the rows where the conditions are met and see if the conclusion is true there. Well, what are the rows where the conditions are met? P or Q, that's going to be true on 1, 2, and 3. Okay. Not P, that's here. That's only true on 3 and 4. Right? So I won't do the two boxes to see where they intersect, but you can see that in order to make both of these conditions true, we're restricted to row 3 here. So row 3 is representing the situation where all the premises are true. And now we just ask, does the conclusion have to be true? Well, the conclusion's Q, which is here. And yeah, there's only one row, and Q is true on that row. And that's it. There's no other possibility. So if those premises are true, the conclusion does have to be true, right? The premises are all true only on row 3, and Q is true on that row. So if the premises are all true, the conclusion must be true. So the definition of validity holds. Let's look at another argument. If P then Q, P therefore Q. And we can just ask, if the premises are true, does the conclusion have to be true? Well, there's only one row where all the premises are true. So if P then Q, that's here, that's going to be true on 1, 3, and 4. And the second premise, P, that's true on 1 and 2. So the only row, we're looking for all of the rows that satisfy the conditions. In this case, there's only one, row 1. And now we're curious, does Q have to be true? Yeah, it does. So that argument is valid. The premises are all true on row 1, and Q is also true on that row. So if the premises are true, the conclusion has to be true. So it's valid. What about this one? If P, then Q, not P, therefore not Q. You might think that's valid. Turns out it's not. But you don't have to worry now about intuition, right? We can just look and see on the truth table. What are the conditions where the premises are all true? It's just 3 and 4. So if P, then Q, that's here. That's true on 1, 3, and 4. Not P, that's only on 3 and 4. So both of the premises are true on 3 and 4. That's premise 1. I'm sorry, this is premise 1 here, and that's premise 2. They're both true on 3 and 4. So we're going to restrict attention to those two rows and then ask, is it possible for the conclusion to be true? Well, where's not Q? That's the conclusion. Does it have to be true? No. It's true here, but it's false there. Row 3 is one of the rows where all the premises are true. So we can see that even if all the premises are true, the conclusion could still be false. So that argument isn't valid. Okay? Not valid at all. All right. So to summarize, to determine if an argument is valid, and I'm going to call this the initial version of the test, because it's going to turn out there's a couple of problems with this, and the rest of Chapter 2 will be just tweaking things to overcome these two problems. But so far, it works, okay? They're not problems with the test, but they're limitations of when we can apply it. And we'll just generalize it so we can apply it all of the time. I'll talk about that in a minute. But to determine if an argument's valid, first you find all the rows where the premises are all true. And then you see if the conclusion is also true on all of those rows. If it is, then that means the argument's valid. It means that if the premises are all true, the conclusion must be true. If it's not, that means the argument isn't valid. It means that even if the premises are true, the conclusion could still be false. Okay? Now I want to talk about the two limitations so far in what we've done. One is that this test is only going to work if the conclusion and the premises are all on that truth table, right? So here's the table we were using. Here's an argument. Can we do this test now? Well, we can't, right? Because if you look up here, premise 1 isn't on this table anywhere, right? If not P, then not Q isn't here. So how could you apply this test? We can't do it. The second limitation is it only works, the way we formulated the test requires that there are some rows where all the premises are all true, right? But look at this argument. Premise 1, not P. Premise 2, P and Q, therefore 3, Q. Well, the test was, step 1, find all of the rows where the premises are all true. Well, let's try to do that. Not P, that's rows 3 and 4 is where that's true. P and Q, that's only true on row 1. So what are the rows where all of the premises are true? There aren't any. Okay? Well, that's a problem because the step 1 of the test was to find the rows where the premises are all true, and there aren't any, so we can't continue on with the test. So these are the two limitations so far. So what we're going to do, starting in the next video, is to generalize this process to overcome these limitations. The first thing we're going to do is learn how to make a table, a truth table that has any statements on it, not just those particular statements that were on that table, but to generate a table that has any statements that we want on it, including sets of statements that have more than 2 atomic statements, right, 3 or 4. then we'll be able to use this test for any argument. Okay. And then we're going to also make a slight revision to how we implement the test so that we can apply it even if there's no rows where the premises are all true. Okay. So those are the two things that we're going to do. But the core idea is legit. That's the way a truth table works, and that's the way we're going to use a truth table to assess argument validity, basically, is we're going to use the table to help us assess whether it's possible for the premises to be true and the conclusion to be false at the same time. And we're going to start with that in the next video.